Alright, I'm back with the shorter segment as you will see. Okay, so in the last segment we obtained, this is very important for the wave equation. When I talk about the initial condition, I have f of x, right? And I also have g of x. So there's a special name if g of x is equal to 0. So if g of x is equal to 0, this is called plucked string. Okay, so if you see this wording, it means that g of x is 0. So is this gonna make your life harder or easier? Well, of course, whenever something is 0, I love it, right? So same thing, this bn drops out over here. Not a big deal. Some books do another analysis just to get this formula. No need. Okay, so just put this bn is equal to 0 in this particular case, and you're gonna get a plucked string. Okay, so I copied this from up there. So the point that I'm trying to make over here is this: what does g of x is equal to 0 means? G of x was del u del t, right? Del u del t. Where is it? Right here. So this is my initial condition. So I'm saying that this is 0. So what this means is this is the velocity, right? Del u del t. At t is equal to 0. So the initial over here, I'm not like pulling it up or pushing it down. I'm simply just letting it go. That's what it means with the plucked string. What I'm going to actually do though is it will be coming from the Fourier series expansion, and it's actually the complex analysis that we have done in the previous segments. And I'll put a link over here so you can watch it if you choose to, okay? But the thing that I'm interested in over here is the angular frequency. So I'm interested in the angular frequency. If I actually go up over here, what you can see, where is it here? From the Fourier series complex, you can see that this was omega t, right? So this was the angular frequency. So I'm gonna simply go ahead and write that. It's gonna be pi Na by L, okay? So from the previous segment. Also, it's important to note that, let's say that I'm looking at the first mode, which means that n is equal to 1, right? So if I put n is equal to 1, I get this one, right? And also I have this a square, which is equal to t over density. T is tension, rho is density. If I plug it in, you're going to say that the first angular frequency is going to be, well, pi by L is there, and a is going to be the square root of this t by rho. Okay? And also we studied this. This angular frequency is 2 pi f. F is the, if I'm using the first, it's called the fundamental frequency. So then I will equate those two. So you'll see that 2 pi f will be equal to pi by L, square root of t by rho. Pi's cancel. I got my first frequency, fundamental frequency, is 1 by 2L, square root of t by rho. I want to highlight that what is this a function of? This is kind of important. So it's a function of the length of the guitar string, it's a function of the density, and it's a function of the tension as well. Now what I want to do is I want to look at the standing waves. Okay, standing waves are something that I do for my research as well. So let's take a look at this. And I'm going to pick up the first fundamental frequency and write my displacement for the first fundamental frequency, and I will get myself a1 cosine of n is 1, right? So it's going to be pi a by L times t plus b1 times sine pi a by L t times the sine pi by L, because n is 1, x. Here I want to highlight to you all is that this is called the amplitude. You heard about this. This is called the amplitude. Why is it called the amplitude? You'll see in a moment, okay? Let's actually go out and draw the string. So let's say we have here, and we go from here to here, and this will be my string, right? So looking at the first frequency, my goal is to find where this whole thing, the displacement, becomes 0. And you can see that this is not a function of x, right? So that's why it's called the amplitude. But this is a function of x. And when I look at it, when is this going to be 0? You will see that in this particular case, I get the boundary conditions actually. When x is equal to 0, I get sine is 0. And when x is equal to L, you can see that, I'll get sine of pi, which is 0 as well. One more item is when u, or the displacement, is equal to 0, we call these nodes. Okay? And looking at this particular shape then, now my nodes will be only where my x is equal to 0 and when my x is equal to L for the first fundamental frequency. So these dashed lines indicate that it's going to vibrate like that, this particular string, for its at its first frequency. So I can do a similar analysis. So let's write over here. This is the first mode. Okay, let's look at the second mode. And in this one, I'll look at u2 of x comma t, and I will get a2, another Fourier series coefficient. I'll get my cosine. Now n is 2, so it's going to be 2 pi a by l t plus b2 sine 2 pi a by l t. Again, still it's the amplitude, it's not a function of x, I don't see any x there, times sine. Now I get a little bit from 2 pi x by l, right? Because n is equal to 2. So again, same conversation that I had here. So this is going to be my amplitude. And looking at this, so where do I get my u is equal to 0? So looking at this, you can see that if my x is equal to 0, I still get 0, right? It's the same as the before, sine 0. Now, if I put x is equal to, interestingly, look at it, L over 2. What happens when I plug L over 2 in here? So I get sine pi, which is 0 too. Okay, so this was new. And the last one is if I put x is equal to L, well, I still get sine of 2 pi, which is sine of 0, which is 0 as well. So now, this time around, I get 3 nodes. So if I were to go and plot this for you, you will see that this is going to be like this. Okay? The vibration is going to go like this. The amplitude will change. Okay? But I will always get a 0 here. I'll get a 0 at L over 2, and I'll get a 0 at L. So those 3 will stay. Okay? So this will be my second mode, right? So I can do the same thing for the third mode, and in order to save time, you will see that this is very similar, except this will be 3, this will be 3, this will be 3, this will be 3, and this is going to call the amplitude, so I'm not going to rewrite that, but it's going to be the amplitude. The displacement will be the amplitude times sine of 3 pi x by L. And if I look at the locations where this is going to be 0, and you will see x is equal to 0 is still there. Let's look x is equal to L by 3. You will see that I'm going to get myself sine of pi, which is 0. I can do also 2L by 3, which is, I'm going to get sine of 2 pi, which is still sine of 0. And I will also get x is equal to L. So I think you can see where I'm going from here. If I have this string, you will see that I will have, let's say this is L by 3. Let's say this is 2L by 3. And if I look at the vibrations, with another color, so it's going to be like this, right? Like this, okay? And again, the amplitude may change. It can be much higher. And I am obviously exaggerating this, right? Because this displacement, as we have covered, cannot be this big. It has to be much smaller than the length, right? But to make a point, I'm showing you these, right? And the nodes that I have is one is here, one is here, one is there, one is there, and the locations is specified as well. Okay, so now this will be handed to you. I'll solve an example in the upcoming segment. Thank you for watching this.